Welcome back to RF Communications. In today's video, we'll explore channel encoders and decoders and see how they help protect data from errors during transmission. Let's get started. Channel encoders and decoders are key blocks in digital communication systems. The encoder adds redundancy to protect data before transmission, while the decoder uses that redundancy to detect and correct errors at the receiver. In this video, we'll see how they work together to ensure reliable communication over noisy channels. Before we understand how channel encoding works, let's look at the problem it is designed to solve. When data travels from a sender to a receiver through a noisy channel, noise and interference can corrupt the transmitted bits. As a result, some bits may be flipped during transmission. For example, a 0 can become a 1, or a 1 can become a 0. These bit errors can cause the receiver to recover incorrect information. To overcome this problem, a channel encoder adds extra bits, called redundancy, to the original data before transmission. These additional bits do not carry new information, but they provide a way for the receiver to detect and, in some cases, correct transmission errors. As a result, the transmitted data becomes more resistant to noise, improving the reliability of the communication system. Channel coding techniques are generally classified into three main categories. First, block codes. In this method, the input data is divided into fixed-size blocks, and each block is encoded independently by adding redundant bits. This structure makes it easier to detect and correct errors. Examples include Hamming code for error correction and CRC for error detection. Second, convolutional codes. Unlike block-based methods, convolutional coding processes a continuous stream of bits. Each output bit depends not only on the current input bit, but also on previous bits, meaning the encoder has memory. This makes it highly effective for correcting errors in real-time communication systems. Third, modern codes. These are advanced coding schemes designed for high-performance communication systems. Turbo codes combine multiple convolutional encoders to achieve near-optimal performance. LDPC codes use sparse parity check matrices for very efficient error correction, while polar codes are known for achieving channel capacity and are used in 5G systems. Now let's look at the opposite side of the system, the channel decoder. The channel decoder is located at the receiver side of a digital communication system. Its main job is to take the received encoded data and use the added redundancy to detect and correct any errors that may have occurred during transmission. By analyzing the structure of the received bit stream, the decoder reconstructs the most likely original data, even if some bits were corrupted by noise. This makes reliable communication possible over noisy channels. Let's understand how the channel encoder and decoder work together using a simple CRC example with data bits 1101 and a generator polynomial 101. We add two zeros because the generator 101 has 3 bitses, so it needs space for a 2-bit remainder. These zeros act as placeholders where the CRC checksum will be calculated and filled in after the division step. Next, we perform binary division using XOR. We divide 110100 by the generator 101 step by step using modulo 2 division. After completing the full process, the remaining bits, remainder, are 11. This remainder is the CRC checksum, and it is appended to the original data to create the final encoded frame. This frame is then ready to be transmitted over the communication channel, carrying both the original information and the redundancy needed for error detection at the receiver. Now, at the receiver side, the channel decoder receives the transmitted frame, but during transmission through the noisy channel, let's assume the 5th bit gets flipped. This means the received data is no longer exactly the same as what was sent, and the integrity of the original information is affected by noise in the channel. Then, the receiver checks the data using the CRC method. It performs the same binary division with the same generator polynomial on the received frame. If the remainder is 0, the data is considered correct. If the remainder is not 0, it means an error has been detected during transmission. In this case, the receiver outputs an error detected message and the frame is rejected or requested to be retransmitted. It is important to note that CRC is only used for error detection, not error correction. This means it can identify when an error has occurred, but it cannot fix the corrupted bits. Therefore, when an error is detected, the system relies on retransmission, where the sender keeps sending the data again until it is received correctly. That's the key idea of how channel encoding and decoding work together using CRC. It helps detect errors during transmission and ensures data integrity through retransmission. If you found this video helpful and learned something new about channel encoding and decoding, don't forget to like the video and subscribe to the channel for more content on digital communication systems. Thanks for watching, and I'll see you in the next video.